Okay, in the previous video, we already looked at two factors, two things that we can do in order to make the reaction faster. And the first one is increasing the speed of the reactants, and the second factor is increasing the temperature of the reactants. Now it's the third factor. The third thing that we can do in order to increase the speed of a reaction is by increasing the pressure of the reactants. Now this factor only works for reactions involving gases. Now, higher pressure. What does higher pressure means? So from the picture here, you can see low pressure. The molecules are far apart from each other. When we increase the pressure, that is when we apply pressure, the gas molecules will be closer to each other. So higher pressure means the reacting particles are closer. And when the reacting particles are closer, there will be more collisions per unit time, and more effective collisions. Okay, actually there should be more effective collisions per unit time. Okay, when there are more effective collisions per unit time, the reactions are formed faster and faster speed of reaction. Okay, remember, increasing pressure of reactants to increase the speed of the reaction only work for gases, for reactions that involve gases, because pressure would have no effect on liquids and pressure would have no effects on solids. Okay, the next thing that we need to look at would be the fourth factor that increases the speed of the reaction, and that would be by decreasing the particle size of the reactants. So if we make the particle size of the reactant smaller, the speed of the reaction would be faster. Now why? Okay, small particle size means what? Means larger surface area. Okay, small particle size means larger surface area. How do we explain this? We can actually explain using Lego. Okay, so there are four Lego blocks here. Now assume that one Lego block is a cube. Okay, a cube means that all the 6 sides have the same area. Let's say this area here is 1 cm cube. This is 1 cm cube, 1 cm cube. So 6 sides, all 1 cm cube. So total surface area would be 6 cm cube. So if we have these reactants, okay, if we have this reactant and the particle size is very small, that means small particle size. So what would be the total surface area? Total surface area would be 6 cm cube, 6 cm cube, 6 cm cube, 6 cm cube. Total 24 cm cube. Okay, now if we have the same mass of the reactant but a big particle size, for example, means like this, one big piece. Okay, one big piece, all the 4 pieces joined together like this form one big piece. What would be the total surface area? So total surface area will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there will be 16 cm square. Okay, total surface area would be 16 cm square. So small particle size, total surface area 24 cm cube. 24 cm square. Big particle size like this, total surface area 16 cm square. So you have 24 cm square, you have 16 cm square, which means that smaller particle size, the total surface area is actually larger. Okay, so small particle size, large surface area. Okay, 24 cm square compared to 16 cm square. Large surface area means more surfaces for reacting particles to collide. When there are more surfaces, it means that when the surface area is larger, it means that there are more surfaces for the reacting particles to collide. Okay, so there will be more collisions More collisions means more effective collisions per unit time. It means that products are formed faster and the speed of reaction is faster. Okay, so this diagram here basically shows the same thing, except that this diagram basically is the same thing. You can find out this is large particle size, one big piece. Large particle size, you can find out the total surface area for the large particle. So the surface with 2 by 1 dimension, 2 cm by 1 cm dimension, how many of them? There are actually 4. Okay, 4. Okay, if you look carefully, there are actually 4 sides with 2 cm by 1 cm dimension. And then plus, there are 2 sides with 2 by 2 dimension. And that would give you 8 plus 8, 16 cm square. So 16 cm square, this is the total surface area of large particle. If we break this particle into 4 small particles like this, so this one will be small particle size. So total surface area for small particle size, so each one, there are 6 cm square. There are 4 of them, so times 4. And that will give you 24 cm. It's the same thing, So you have 24 cm square, you have 16 cm square. So smaller particle size, larger surface area. Larger particle size, smaller surface area. Okay, so surface area is very important because it determines the surfaces for the reacting particles to collide. So when the surface area is more, it means that more surfaces for the reacting particles to collide. More surfaces to collide means that there will be more collisions and more effective collisions, hence faster speed of reaction. Alright, so that would be the 4th factor. Now let's look at the graph here. Now this is the graph plotted volume of carbon dioxide produced against time. Okay, it's the same thing as the reaction between the hydrochloric acid and the marble chips. So you will get, you have a carbonate, you have an acid carbonate, you get salt, in this case is CaCl2, plus carbon dioxide plus water. So we measure the amount of carbon dioxide here. Okay, balance the chemical equation. Now you have a small chips. So this is the curve for the small chips. This is the curve for the large chips. Okay, this is reaction 1, large chips. This is reaction 2, small chips. So which reaction is faster? Reaction 2 is faster or slower? Reaction 2. So you have to look at the gradient. Is the gradient here steeper than this? Okay, reaction 2 is actually the gradient is steeper. Gradient is steeper means the reaction is faster. Why is it faster? Because of the smaller particle size. Hence reaction 2 is completed. Now when the reaction 2 is faster, right? Means that the reaction will be completed faster. At what time? What time does the reaction complete? So from the graph, the reaction is complete when the graph becomes horizontal or when the gradient becomes 0. So there will be 2.5 minutes. 2.50 minute. Okay. Now why do both reactions release the same? So from the graph here, the question actually I ask you, why do both reactions release the same amount of gas? Why? So the reaction actually the question tell you both of this experiment, both of this reaction, they release the same amount of gas. Okay, they release the same amount of gas because the amount of gas here is the same here. Why? So remember, the amount of product produced in the reaction is determined by the amount of by the amount of limiting reactant. But in this case, there is no information that allows us to find the amount of limiting reactant. So what we can do is, because the same amount of HCl and CaCO3 are being used, okay, same amount of HCl and CaCO3 are used. We don't know which one is limiting because there is no information given. So we just say that the reactants are the same amount. Now the fifth factor that affects the speed of reaction is actually catalyst. Now a catalyst is a substance which increases the speed of a chemical reaction without itself being chemically changed at the end of the reaction. So that would be a catalyst. It's a substance which increases the speed of a chemical reaction. So there are 5 factors that can affect the speed of reaction. You have concentration of the reactants, you have temperature of reactants, pressure of reactants, the particle size of reactants, as well as catalyst. Now the last part of the mind map touches on sketching of graph. Now all these 3 graphs here is based on this chemical reaction. Hydrochloric acid and marble chips, you get CaCl2, CO2 and H2O. Now, the height of a graph, when you plot or when you sketch the graph of the speed of reaction, there are 2 aspects of the graph that you must get it correct. First one is the height of the graph. Now, the height of the graph actually depends on the amount. The height of the graph basically represent the amount of the product form. Height of the graph represent the amount of the product form. When the graph is very high, it means that more products are formed. If the graph is very low, it means that it's very low, it means that the amount of product form is very little. And the amount of product form depends on the amount of limiting reactant, like what I mentioned in the previous page of the mind map, depends on the amount of limiting reactant. If the amount of limiting reactant is double, the height will be double. So the height of the graph, very important, depends on limiting reactant. If we double the amount of limiting reactant, the height will be doubled. And likewise, if we halve the amount of limiting reactant, the height of the graph will be halved. Now the second aspect of the graph of the speed of reaction that you need to take note of would be the slope or the gradient. The slope of the gradient basically represents the speed, how fast the reaction is. The steeper the gradient, the faster the speed of reaction. And likewise, the more gentle the gradient, the slower would be the speed of reaction. And this gradient depends on the factors that affect the speed of reaction. Okay, the 5 factors that we mentioned just now. The concentration. So higher concentration, it means that the graph will be steeper. So concentration, as in the mole concept chapter, they are usually in the units of mole per dm cube or gram per dm cube. So high concentration, steeper. High temperature, steeper. Smaller particle size, that means for example powder form, they'll be steeper. High pressure for gases, they'll be steeper. And of course, if catalyst is being used, that would be steeper as well. Now, by the way, let's say you're given 2 curves. How do you know which one is steeper? You can actually just imagine that you put a ball here and put a ball here. Which one will roll down faster? The one that will roll down faster, the curve will be steeper. Okay, if you put here, for example, if you put a ball here, compared if you put a ball here, of course this one, it will roll down faster because the drop is sharper. Okay, so the ball here would just plunge. And this one roll down slower because the slope is more gentle. So you have to learn how to find out whether or not the graph is steeper or is more gentle and things like that. Just imagine you put a ball on the curve. Now let's look at this, the first example. Sketch the graph when the following is used. Now this is the original graph, original curve. 2 mole per dm cube HCl at 20 degrees Celsius. Now if I conduct another experiment using 3 mole per dm cube of HCl at 30 degrees Celsius, what would be the speed of reaction curve? How would be the speed of reaction curve look like? Now first of all, compare 2 mole per dm cube, this is concentration. this is temperature. So this one has higher concentration, higher temperature, which means that the speed of the reaction will be faster. Okay? The speed of reaction will be faster, which means that it is steeper. So if you sketch the curve, so the curve will look something like this. Okay, the curve will look something like this. Okay, my drawing is not very good. Okay. Make sure the curve is smooth. Yeah, so this one is 1A. Now there will be questions on this in O level, so make sure your curve is smooth, and remember, do not draw like this, do not sketch like this. This is art. Well, chemistry is not art, so your curve must be smooth, cannot be like this. This one will be marked wrong. Okay, so there will be 1A. How about for 1B? 1B is 3 mole per dm cube, same thing, 20 degrees Celsius. So if you compare A and B, which one is faster, the speed of reaction? Of course A is faster, B is slower, but B would be faster than this. One thing to take note of for A is that the reaction is faster, right? Because the concentration is higher, the temperature is higher, which means that the reaction will complete faster. It will become horizontal faster than this. This one will become horizontal around here. So 1A, since it is faster, it will become horizontal around here faster. Okay? So the speed of reaction for B, for 1B, would be in between these two. So make sure you draw it correctly, in between. Okay, so it would be something like this. Something like that. So this is 1B. Of course, I'm not using, I need to be fast in this video, so my graph is not perfect, but you should be able to draw better than me because my hand is kind of shaky. Young people's hand are not shaky, so you can do better than me. Okay, so this is 1B. How about 1C? 1C, 1 mole per dm cube. If you compare this, 2 mole per dm cube, 1 mole per dm cube, see, the temperature is not given, which means that for 1C, the temperature is the same as the original one, which is 20 degrees Celsius. So lower concentration, which means that 1C would be slower, the speed of reaction would be slower than this one. So slower means less steep. Less steep means that the reaction will complete. Slower reaction means that the reaction will complete at a much later time. So it would be something like that. Like that. Okay? So this is 1C. Alright? It is very gentle. It is more gentle than this 2 mole per dm cube. And because of that, it will the reaction complete at a slower, at a later time, much slower compared to 2 mole per dm cube. So the reaction only complete at this time, compared to at this time for 2 mole per dm cube. Alright? So remember, when you sketch a speed of reaction curve, make sure the curve is smooth. Number 1. Number 2, take note of the height of the graph as well as the gradient. Number 3, make sure you label it. And also, it must be very distinct between the graphs. So do not draw like this. Let's say for 1B, do not draw like this. Okay, the difference is so small. Such a small difference between 2 mole per dm cube and 1B. Don't draw like that. Make sure the difference is very stark. It's very, very clear. Okay? Now let's look at number 2. Okay, number 2, This is 0.5 gram calcium carbonate reacts with excess, excess HCl. It means that this one is limiting. This is the limiting reactant. 0.5 gram calcium carbonate. So the amount of limiting reactant is very important because that would determine the height of the graph. So if you look at 2A, 0.5 gram calcium carbonate, same amount of limiting reactant, which means that 2A and this one have the same height. How about the speed? 2 mole per dm cube. This is 1 mole per dm cube. So 2A will be faster. So 2A is faster, same height. So it would be something like this. Oops. Okay, this is not very smooth. Okay, you can draw better than me. Again, I don't have any eraser with me. So this is actually 2A. Okay, same height, faster. Now how about 2B? 0.25 gram calcium carbonate. This is half the limiting reactant here, which means that 2B would have half the height of this one. How about the speed? Same speed. Same speed means same gradient. So at first, they will have the same speed. Same speed because same gradient. Same speed, same gradient. Then after that, the height would be about half. So it would be something like that. You can see the height here. The height here, let's say the height here is, let's say for example, this one is 2. This one would be 1. But of course you don't have to label it because this information is not given to us. So this is actually not very horizontal. Again, you can draw better than me. This one should be perfectly horizontal. So this is 2B. Okay? Now let's look at number 3. Sketch the graph when the following is used. Lumps of calcium carbonate. And again, if you look at the original one, excess lumps of calcium carbonate, excess, which means that HCl is limiting. Lumps of calcium carbonate, 1 dm cube, 2 mole per dm cube HCl. Now, very important. 2 dm cube, 1 mole per dm cube. If you multiply these two numbers, what do you get? If you multiply these two numbers, the dm cube and the dm cube will cancel off. That will give you mole. So if you multiply 2 and 1, you get 2 mole. 2 mole of HCl. Oh yeah, one more thing I need to point out is that when you sketch the graph, you must use pencil. That's why I'm using pencil now. Must use pencil when you sketch or when you plot a graph. I say it again, must use pencil. So when you multiply these two numbers, you get 2 mole. 2 mole of HCl. So 2 mole of HCl. How about this? 1 mole, 1 dm cube, 2 dm cube. Same thing. This is 2 mole. 2 mole of HCl. So the limiting reactant have the same amount. 2 mole and 2 mole, same amount. Meaning that they'll have the same height. How about the gradient? 20 degrees Celsius, 20 degrees Celsius. How about the concentration? 1 mole per dm cube, 2 mole per dm cube. So 3A is more concentrated, meaning that it would have a steeper slope, steeper gradient. Steeper gradient, same height because same amount of limiting reactant, So your 3A would be like this. This is your 3A. Okay? So it become horizontal. Since the reaction is faster, it should become horizontal faster. How about 3B? 3B is powder. This is lump. Lump means very big piece. this is powder, which means smaller particle size. Smaller particle size, the speed of reaction will be faster. So smaller particle size faster, also higher temperature, also faster. Concentration, same. So higher concentration, smaller particle size, so 3B would be faster. Okay, 3B would be faster. How about the amount of limiting reactant? These two numbers, if you multiply together, you get 1 mole. See, the amount of limiting reactant is lesser, which means that 3B, the gradient is steeper than the original one, but then the height is only half. Okay, so it would be something like this. Okay, steeper than the original one, but the height is actually half. Now this is actually not really half. Okay, let me get an eraser. Okay, where is my eraser? Okay, I found it. Okay, it's actually not this. Okay, it should be something like this. Well, this is still not half. Okay, it's about half. So the height of this graph should be half compared to the height of this. Yeah, roughly that's like that. 3B. Okay? Okay, how about the fourth one? Now, all these three graphs, they are all curved up. This one is curved down. So this one is for another reaction. Why is it curved down? Because this is measuring the mass of the entire system. The mass of the system will decrease because of the escape of carbon dioxide through the cotton wool. That is why the balance reading, the mass of the system, will decrease. Now let's look at it. Sketch the graph when the following is used. Powdered calcium carbonate, powdered. This one is lump, powdered, smaller particle size, right? Smaller particle size, so it will be faster. 4A will be faster. How about 2 mole per dm cube? 2 mole per dm cube, same concentration. How about temperature? Temperature, higher temperature, so it will be faster. Higher temperature, smaller particle size, so 4A would be faster. Okay, 4A would be faster. So it would drop like this. Okay, it will be steeper. Then after that, it would go back. There is no mention on the amount of limiting reactant. Limiting reactant in this case is calcium carbonate, but there is no information that enables us to find out the amount of limiting reactant. Okay, see, concentration, you cannot get the amount of limiting reactant, you cannot calculate the amount of limiting reactant from the concentration and temperature alone. So we are assuming that the amount of limiting reactant is the same. So the balance reading will drop back to the same. So this one will be 4A. Alright, now let's look at the last question. 1 mole per dm cube HCl or 1 mole per dm cube H2SO4, or this one will react faster. Will react, I think that there's something wrong here. Will react faster with calcium carbonate. So which one? Explain. So which one will react faster? Now remember, this is a reaction that involves acid and carbonate. So it depends on the amount of hydrogen ion. Any reaction that involves acid, you have to look at the amount of hydrogen ion. The acid that has more hydrogen ion would be the one that react faster. So in this case is sulfuric acid. So sulfuric acid is a dibasic. Remember? So we answer the question first. So which one will react faster? That will be 1 mole per dm cube H2SO4. Now why? Because every 1 mole H2SO4 produces 2 mole of hydrogen ion. Okay, compared to 1 mole H plus from HCl. So there are more hydrogen ion. There are more H plus to react with Mg, and that resulting in faster speed of reaction. Okay, so it depends on the amount of hydrogen ion. H2SO4 is a dibasic. HCl is a monobasic. Okay, that would conclude the speed of reaction mind map. Thank you for watching.